Hello, welcome to chapter 24, which is going to be the last chapter that we go through for this year. It's the last chapter that will be included on the AP test this year. If you have your textbook with you and you flip through it, you'll see that there are 26 chapters in the textbook, and you can look through the last two chapters if you would like. If you're going to take more stats courses as you go on through your education, it might be useful to look through those chapters and see what's going on there. Especially chapter 26, which deals with regression in a little more detail than what we talked about earlier in the year. But since the AP test will only cover through chapter 24, and I want to make sure we have plenty of time to review before you take that test on May 22nd, which is the date for that, I want to make sure that we're good through everything that will be on the test, and this will be the last concept that is covered. So, let's take a look here. We've got 10 men who volunteered to test an exercise device from an infomercial 3 times a week for 20 minutes. Okay, so someone is bankrolling this experiment, and they are doing this experiment to determine whether this device, this exercise device on this infomercial, is effective. Okay, so 3 times a week for 20 minutes, these guys are going to use this device, and we're going to measure their resting pulse rates. So similar to what we talked about in the last chapter, it's a similar example with the same variable, resting pulse rates. They were measured before and after 6 weeks as part of a randomized experiment. So we've got 10 guys here with varyingly amazing names, and we've got their resting pulse rates before the 6 week exercise program and after. And I suppose, well, let's look at the question here. Is there evidence that this kind of exercise can reduce resting pulse rates? If so, by how much? So this requires a little bit of knowledge of resting pulse rates. The lower, the better, for the most part. If you've got a resting pulse rate in the 90s, let's say, that's probably a little high. You want that to be a little lower. And one of the ways to do that is exercise. Okay? So what they're trying to find here is this exercise device successful in getting people's resting pulse rates down to a more acceptable level? Most of these are on the high side. Okay, so based on this question, you might, by this point in the course, be pretty used to the fact that, yeah, we're going to be doing a hypothesis test to answer this question. And if we reject the null hypothesis, we would need to answer this question by calculating a confidence interval. So we know in general what we need to do here. How many data sets do we have? Well, we've got everyone's before and everyone's after. So we've got 2 samples here, 2 different data samples. It wouldn't be right to put all of these into the same one because we want to make sure that this one is different than this one, that they are separate data sets. So can we just do the same test that we did in the last chapter, where we do a 2 sample test? Well, think about the conditions for that test. Randomization, 10%, large enough sample, or nearly normal. They had to be independent groups. Are the 2 data sets here independent of each other? I don't think so, because for every value in the before data set, there is a corresponding value in the after data set that represents the same person. These 2 data sets are not independent of each other. So we actually can't use that 2 sample test because it assumes the groups are independent of each other. Since that's not the case here, we're going to have to do something different, which is why this is in its own chapter. Okay? And what we're going to do here, well, let's think. If the groups aren't independent, that means they're somehow related, right? So what's something we could do with these two data sets, since we know they're related to each other? We want to know if the pulse rates are reduced. So we're trying to compare these two data sets. How could we determine if the resting pulse rate has been reduced? Well, we could take the difference between these, right? We could take the after pulse rate and subtract the before pulse rate for all these guys and see if there is a significant difference. That's exactly what we're going to do here. We're going to turn these two paired data sets into a single data set that is just the differences between the two. So we can't use the two-sample t-test because the data sets are not independent. Okay, so wherever you're writing your notes, I hope you're writing notes down somewhere, whether it's in your composition book or on paper. You will probably want to remind yourself why we're not just doing a two-sample t-test here. It's because the data sets are not independent. If you didn't write that, maybe you would have seen that as you check conditions. Okay? But that is why we're going to use what's called well, we're going to spell it correctly. That would be important. It's paired. This is called a paired t-test, and we're going to use that instead. Okay. This is for when you have two data sets that are related somehow, that they are not independent. You see this a lot with before and after in terms of experiments. You see it with, say you're studying something about families and you've got data from different people in the same family. You can't assume that whatever it is you're measuring is necessarily independent with two people that are living in the same place. Okay, if I wanted to know what the effectiveness of social distancing was, and I sampled different people from the same family, chances are those people are hanging out together. So whatever data I get from those individuals would not be independent because they're together. So in situations like that, that's why this test exists. Okay, so what we're going to do is we're actually going to, in our little bit of space here that we have, we're going to calculate differences. And there are a couple different ways to do this. With a relatively short data set like this, with numbers that are fairly small, you could probably just do it in your head and write down the differences here. What you could also do, and this might be a little more helpful because you're going to have to put this in the calculator anyway, go ahead and put this data set in L1, make these numbers L2, and then you can calculate the differences in L3. And I'll show you how to do that in just a sec. If you want to pause the video and put those in L1 and L2, I'll show you how to get the differences really easily in L3. Okay. So you've got your L1 and L2. Those are our numbers there. In L3, you need to scroll up so that L3 is highlighted and hit enter. Okay, now put your cursor down there at the bottom. It's blinking where it says L3 equals. We want to take after minus before. So we want to take L2 minus L1. So to get L2 minus L1 down there at the bottom, to get L2, that's going to be second, the blue second key, boop. And then the number 2. See how it says L2 above the number 2 there? Oh my gosh, this is so bad. My apologies. It says L2 in blue right there. So if you just press second 2, boom, L2. Minus second 1. So we've got L2 minus L1 there. If we hit enter, it'll automatically fill in L3 with those differences. If I were an expert video editor, I would cut in like a virtual version of this calculator and how to do all that. I knew this. Sorry, this is all you get. So I'm going to write down these differences. You wouldn't necessarily have to do this. But this is one of the few types of hypothesis tests or confidence intervals where they would probably give you the raw data, because you would have to take the differences of the raw data in order to do this test. So this is going to be -2, 1, and -3. Okay? Right. So, we could start with conditions, but again, with hypothesis tests, I think the important thing to start with is the hypotheses themselves. That just gives you a really good foundation for knowing what type of test it is that you're doing, so you can check the correct conditions. So our null hypothesis here, the status quo, the thing that would not be very interesting to learn as a result of this would be that there's no difference between the before and after pulse rates. So we've already calculated the difference. So really, now that we've calculated this, we will only be using this data set, which is an L3 in your calculator. This is all we're using now, because in here we've got all of this information already in here. So we're only dealing with this. So we're going to say that the null hypothesis is that the mean of these differences, which is usually denoted mu d, this is the population mean of all possible differences for the entire population. The null hypothesis would be that that is equal to 0, that there is no difference, truly, in the population. What might the alternative hypothesis look like then? Well, we know it has to be about the same parameter, and that has to be the same number. But what sign is this going to be? I'm looking up at the question. Is there evidence that this kind of exercise can reduce resting pulse rates? So ideally what we would like to see here is a negative value for the difference, since we did after minus before. So we actually want this to be less than 0. Less than 0. Okay. So again, as we go through this test, we're only going to be using this set of data, the differences between the two values. Okay. And if you're thinking, well, if we're only looking at this data set, then what's the difference between this and a regular t-test? Well, there isn't a whole lot of difference at this point. Let's see here. Now that we've got our hypotheses, let's check our conditions. I'm sure you could give me at least one or two off the top of your head. Randomization. Now, there is a little bit of a wrinkle with this example in terms of the randomization condition. Do we need a random sample? Because we don't have one. How did these guys get into this study? They volunteered. Does that mean this condition is not met? This one? Whoosh. No, because it only needs to be a random sample if you're doing like a survey. This is an experiment. So as long as the experiment has randomly assigned treatments, then this condition is met. And it does say that this is part of a randomized experiment. Okay, so perhaps this was a much larger study and other people got different numbers of times per week of exercise, or maybe a longer or shorter amount of time per exercise period. This is just all the people who had this particular treatment. So for randomization, you could say something like from the prompt randomized experiment. And that is good enough for that condition to be met. Another one, 10%. Still applies here. So we might say something like, we only took 10 men here for our sample. 10 is less than 10% of all men who may use this exercise device. Okay? I suppose the population could be considered to be all men, period. But in particular, we're looking at ones who would use this exercise device. Maybe they're men that have high resting pulse rates already. Okay, randomization 10%. I already kind of gave you a little hint. This is going to be a t-test still. So after randomization 10%, this third condition is the large enough sample condition. Okay. And remember, this condition says if your sample size is at least 30, you're good. The central limit theorem kicks in and you can assume that those differences follow a nearly normal model or a T model. But our sample size here is a little smaller than that, n equals 10. So in order to show that this looks nearly normal, we have to make a histogram, which is why I suggested that you put this in your calculator. So we need to make a histogram of these values, which if you did this as I did, this is an L3. So you will go to the second stat plot. You can use that first one there. Make sure that plot is on. Make sure it's the histogram, which is the one that is highlighted here. It's this one. And make sure your X list, usually it's L1, but remember in this case it's going to be L3. It's that data set of differences in L3. And that frequency is always 1. At least for this example. For most of the examples that we would ever do. Okay. Once you've got that, you can zoom 9. That gives me this. Now that seems kind of odd. Why is that axis going through there like that? Well, think about what our variable is. It's the differences between those two data sets. You've got a lot of negatives here, but you do have a 0 and a 1. So that axis there is actually 0. Okay. Now, sometimes I like to fiddle around with the window on the calculator, especially if I look at it and I see that the X scale is something odd. But what I see here, again, we're trying to check the large enough sample condition or the nearly normal condition. That looks all right to me. I'm going to take a quick sketch of what this looks like. Okay, it doesn't have to be super detailed. You can break the rules about needing to have a title and the axis labels and all that. This is just a sketch to check this condition. Okay. You need to check several things, whether this is unimodal. I'm going to go ahead and check that. Don't fall into the trap that just because you've got two bars here that are the same height, then that means that this is somehow like a bimodal curve or something. It's not. Plus, this is just a sample. We're trying to figure out whether this sample looks like it could reasonably come from a normal distribution. Okay? Does it have that general shape to it? The smaller your sample size is, the more leeway you can give here. So I think it's definitely possible that this curve actually looks something like this. And I shouldn't have put my axis here. It's actually here. But you can see it does have that general shape. So I would consider that unimodal. Is it perfectly symmetric, like a normal curve or a T-curve? No. But it's reasonably, those peaks are not like at one end or something. You can see that curve going through there. So I would call this roughly symmetric as well. And we also want to make sure there are no outliers. Okay. It's not like we have an individual here where the difference was like -12 or +8 or something like that. Okay. All of these are pretty tightly packed in here. So, it appears as if all of these conditions are met, and those are the only conditions for this test. But the thing to keep in mind here, once we've taken the differences to perform this paired t-test, everything we do for the test is based on this data set, not the ones that you were originally given in the problem. The hypotheses only have one parameter here because it represents the differences. This condition, you're checking based on the differences. Going through the mechanics of the test, which we're about to do, we're only going to be using the differences. So we're essentially treating it like a one-sample t-test, the first kind of t-test we ever did. But that sample is now the differences. So let's keep going. Since all the conditions are met, we're going to use a paired t-test. I might even put all conditions are met. All right. So we might want to calculate, well, this is the point where I would usually draw my t-model if I knew I was doing a t-test. It's good enough for me. It doesn't look great on video. Looks better in person, trust me. This looks fantastic. This is going to be the number in the middle. So again, we need to find our t-score as a frame of reference for where we're going to be shading and all that to find our p-value. So we need to find our t-score. So we need the value that we're interested in here, which is the sample mean of the differences. So I'm going to call that x bar d. This is the sample mean of the differences. We're going to subtract the mean from the null hypothesis. So I'm going to use the original notation here from our t-test in the past. This is mu naught. That is the value of this number here in the null hypothesis. We're going to divide by the standard error. This is going to be the standard deviation of the differences of this data set over the square root of n, just like last time, just like our t-scores in the past. So we know some of these things already. We know that this number is 0, and we know that the sample size is 10. The mean of the differences and the standard deviation of the differences, I haven't calculated those yet, but we can get those from going to stat calc. It's our good old friend, one-var stats. There you go. One-var stats. But you can't just hit enter there. You need to show that it's in L3. So you just need to put L3 right in there right before you hit enter. At least that's the way it is on my calculator. Yours might be a little different, but you have to show that it's this data set you want the mean of. Otherwise you're going to get a mean of like 80 something, and that's not going to be good. Okay, so what I get here is that the mean is -2.8. which if I take a quick look here, that makes sense, negative 2.8, with a standard deviation, that's Sx, not sigma x, of 2.53. 2.53. So you can go ahead and calculate your t-score there. Sorry about that. My cat is really annoying. So, we calculate our t-score here and we get, what does that give us? About negative 3.50. Negative 3.50. This is a relief to me that we're getting a t-score this small, because that means that our t-score is down here somewhere. And we're shading in what direction? To the left. Thank goodness. If our t-score was somehow like positive or something, and we were shading to the left, that'd be a huge p-value. Be a huge p-value. That's not what we want. That's right. We want a small p-value. So, we want to find out what this area is. This is where TCDF comes into play. TCDF. So that's second dister, TCDF. Now, you would not write this on the AP test because remember, those boomers don't really care about what you're typing into your calculator. I'm just writing it here to show you what you would need to input. You need to start with the t-value that is the smallest one that you're interested in. That goes way off to the left at negative 9999. And it goes up to negative 3.5. TCDF also asks for the degrees of freedom. Now, are we going to run into the same problem we did with the 2-sample test where the degrees of freedom was like this nasty decimal that we couldn't find unless we used a calculator? No. This is very similar to the 1-sample test. We now only have this data set to look at. What's the sample size? Ah! Sample size is 10. So our degrees of freedom is n minus 1 again. So our degrees of freedom should be 9. 9 degrees of freedom. Cat, sometimes you just scare me. 9. So we are using TCDF to find that area. And I get something along the lines of 0.0034. Is that what I got last time? Yeah. All right. I love it when it works out. I get 0.0034 there for the area. So that is the p-value. What I would like you to do at this point, if you need to go through any of those steps again, one of the great things about doing class this way is that you can pause and rewind the video if you need to go through some of that again. But essentially, this is just a 1-sample t-test with our differences as the data set. Okay? What I would like you to do now is to take what we have found with our p-value and write your decision and your conclusion. What is it you're saying about the null hypothesis, and what does that mean in context? So go ahead, pause the video, take a minute or two, write that out. So there we go. We're comparing our p-value to alpha, which once again I have neglected to tell you what it is, mainly because I didn't know if I would have enough room on my board to put everything on here without having to erase anything. So since we don't know what that significance level or alpha level is, we assume it's 0.05. Our p-value is smaller than that, so we reject the null hypothesis. Yay, that's what we wanted to do. We want to reject the null hypothesis usually. And that means that there is evidence of what the alternative hypothesis is saying, which is what the question is asking. There is evidence that this kind of exercise can reduce resting pulse rates. You may have had an idea that that was going to be the case, given that most of our differences here were negative. But remember, you have to go through the test to determine whether the mean difference or the mean of this data set is far enough away from zero to be significant. And it is in this case. Okay. So, now that we've rejected the null hypothesis, we know that there is a difference between the before and the after. How much of a difference? Well, that's what we would calculate we just did a hypothesis test. That's how we would answer this using a confidence interval. And since this video has been going on as long as it has, I think I'll just stop there and we'll tack that on to the beginning of the next video. So, for me and for my kitty cat, I hope you enjoyed this video. I hope you learned something about paired t-tests, and we will see you again next time. See ya.